Okay, I think we'll get started. So welcome everybody to this Wednesday webinar, BAA webinar. I think they've turned out to be very popular. They started as a kind of emergency response to the COVID, but I think generally they've worked out really well, and people are still keen for them to continue even when we start getting back to more normal meetings. So tonight we've got a really interesting talk, and I say that in a biased way because I'm obviously really interested in comets, and Comet 67P Schwassmann Wachmann is probably one of the most interesting comets there is. So we've got two speakers tonight. We've got Richard Miles, who I'm sure everybody knows. He's the director of our Asteroids and Remote Planet section. He was a professional chemist and retired, and then became an almost kind of semi-professional astronomer, and has been running the Mission 29P project for the BAA Comet section, which involves monitoring 29P, and Richard will explain why that's important. But we're also really pleased to be joined by Professor Laura Woodney from California State University. Professor Woodney's been involved a lot with 67P, and particularly with
29P.
29P, why do I say 67? That's Cherry Mulgarisamane.
Yeah, we were just talking about 67P just before we came on, yeah.
Daily numbers, yes, 29P, sorry about that. Has been involved in a lot of aspects of that Centaur comet, particularly a NASA Discovery class mission called Chimera, which has the opportunity to actually send a spacecraft to 29P and look at it close up. So Richard, I'll hand over to you now. As normal, we'll take questions. You can either raise them on Zoom, or if you're watching on YouTube, you can raise them in the comments, and we'll take the questions at the end, and I'll pass them to the speakers then. So Richard, do you want to go ahead?
Share screen. Hang on, let's see.
I'll mute myself so I can sit here quietly whilst everything's going on.
Can you see that? Does it come on?
Not yet.
Oh, okay, I think I have to start it from here. That's right. I got it. Right.
There you go. It's coming. So it's not full screen yet, but if you just go into...
Yeah.
Your subscription has expired.
Yeah, don't worry. Great. Okay, you can see I call this a superactive Centaur, and to me, it's really quite unusual. It's convinced that there are cryovolcanoes and possibly cryogeysers, two types of active source on the nucleus. So I'm going to tell you something about the story as it is so far. So it was discovered in 1927. And Arno Schwassmann and another Arnold Wachmann, they picked it up on a photographic survey. Most of the comet work was done with photographs, and they found it magnitude 13 when it was in outburst. And really, over the following decades, this photographic studies were exemplified by Elizabeth Romer's images that she published, showing basically that it starts from a star-like point. The comet gets very bright as a star-like point, and then a coma appears, often asymmetric, and it expands. Now, surprisingly, there's another character in this story, and that's Fred Whipple, because Fred Whipple could be considered one of the fathers of cometary astronomy. And his career was actually bookended by Comet 29P. When he was a student first in his undergraduate years, he actually, in 1927, which is when it was discovered, he actually got involved with Lick with calculating its orbit. And his very first publication was in the Lick Observatory Bulletin in 1928 on this very subject. And his very last major publication was 52 years later in the Astronomical Journal, where he tried then to use all the data known to solve the enigma that is 29P, but failed miserably, sadly. And Fred left us in 2004. He was the one who coined the term for comets as dirty snowballs, which people have translated now to icy dirt balls. But 29P, let me tell you, is nothing like either of those things. It is a centaur, it's not a Jupiter family comet. Okay, so let's fast forward to the start of the 21st century and the thing that makes the difference for amateurs, and that was the arrival of CCD cameras, but in particular of a chap called Herbert Robb, who wrote the software called Astrometrica. And it was around the 2002 time that catalogs, star catalogs, comprehensive ones, became available. And Herbert used these, which crucially then allowed amateurs to measure the positions and brightnesses of comets very accurately. Now, back in 2002, 2003, they would report these to the Minor Planet Center, and they would use all sorts of different size apertures to measure the brightness. And this meant that if you plotted out the data that they produced, you got quite a lot of scatter, but you could see that this comet was having these outbursts and occasionally double outbursts. Now, from 2014 onwards, things changed because a few people, including myself, got involved with trying to do this photometry more accurately. I'll go on to talk about that. But let's just look at the orbit of Comet 29P. And I think Laura's going to talk a lot more detail about this. I'll just show you that most cometary orbits are elliptical, Halley, Comet Holmes. And the Jupiter family comets are sort of constrained by, this is the orbit of Jupiter. So the aphelia of these comets is near that of Jupiter. But 29P, as Fred Whipple found out when he was just a 19-year-old, so he found that it was in a circular orbit just beyond that of Jupiter, and it was actually held by the gravity of Jupiter and Saturn, and it's held in this. And recently, professionals have published papers where they talk about this region as the gateway region, and Laura will tell us more on that. Okay. Now, I'll show you a few good views of close-ups of what 29P looks like when it's in a strong outburst. Here's one example taken with a 2 meter. So you can see actually the results of 2 outbursts separated by just under 2 weeks. There's an inner coma and an outer coma superimposed. But these 2 comas, are expanding all the time. And Damien Peach has produced a nice composite picture of what a single event evolves to in this set of composite images where they're all superimposed on the same frame. And what you see is that unusually is that there's a notch seemingly taken out of the coma. And this is actually a strong indication that the nucleus is a very slow rotator. We call this a Pac-Man shape, if you remember the computer game Pac-Man. And it is an indication that the source of the outburst is from near the morning terminator on the nucleus. Now, 2014, as I say, was when we began investigating it in more detail. Oh, sorry, just one more. This shows again, this asymmetric outburst and the fact that the outburst is coming from one side of the nucleus, i.e. the morning terminator. Now, since 2014, and these are the 2014, 2015, and 2016 light curves, this is the sort of activity which, plotting them, reduce magnitude against time for each apparition. And I think you'd agree with me that this isn't a sort of random collection of data. There's some sort of pattern or periodicity on this. Now, if you analyze it using a smaller aperture, you'll see that there actually are, down here at the red line, is you can see these, what we discovered were mini outbursts that are happening. And this is a new class of outbursts which had been missed before 2014. And we'll see is quite common. We've seen lots of them in more recent times. By then, 64 outbursts had been logged from the MPC, the Minor Planet data. And I did a study and published in Icarus a tentative rotation period based on data. These are 26 of those 64 outbursts. And when you analyze those from 2010 to 2014, you could find a periodicity in them. And what you see is a fundamental frequency, which is of about 57.5 days. You also get a secondary peak, which is actually a harmonic at about 68 days. And what that is, it's a harmonic created by the fact that there's a synodic period of 392 days. And this is the calculation now that shows the relationship between the 67.8 and this equates to a 57.8 period because of this synodic repetition. So, okay, so that data shows this periodicity. Let's now take all the data. I'll jump much further forward and take the data that we've gathered since 2002. So the first half of this is showing on the y-axis. It's taking a period, an assumed period of 57.7 days. And it calculates from the time of each outburst what the phase would be in the rotation between 0 and 1. Okay, and then you plot that out over the 18 years or so, over the intervening time, and you get this unusual pattern. One actual orbit of the sun by the comet is this amount. So in that time, you might see 4 seasons. But we only actually began intensive observing at this point, where it's shown by the blue dashed line, and see how all of the very faint outbursts have all been seen more recently. And before that time, they had been overlooked. Okay. Now, if you look on there, you will see areas which have a paucity of strong outbursts. So I've outlined there one such area. And I outlined in yellow here another. And you can see that this period seems to separate out the data in a quite remarkable way. And it's actually quite strong proof of the period being a correct one. It's not the only proof. If you were to change that period, what would happen? So the next one is the same data plotted on a 17-day period. See how the strong and the weak outbursts get mixed up, or change it to 31 days. See again, there's no real structure or pattern to that. If you take half this notional 57.7 day period, again, nothing comes out of it. So we're left coming back to this particular one, which seems to show something very special. And indeed, it shows possibly a seasonal change between weak, strong, and weak. Now, another way of trying to see whether outbursts spaced by about 58 days are related is to actually look at the flows in the inner coma. And these are 3 examples of pairs of outbursts where we have actually exaggerated the outflows by doing a rotational filter analysis. These are generally 2-meter aperture images. And you'll see that you get a repetition of a similar pattern. It's like a fingerprint due to the flows. And that therefore indicates that the same source is outbursting on a second rotation of the nucleus. So keep that in mind, that's an important thing. You have very slow rotation, you have very long daytime and very long night times. Okay. Right, I'm going to finish off shortly before I hand over to Professor Woodney And I'll just say a few things about the latest apparition. And we've set up what we call the mission 29P. I set that up because it was very disappointing that a proposal for a space mission to NASA was turned down, and I decided the amateurs needed to up their game and do more observing. So the next plot is the latest apparition that has just finished last month, and it shows the all 1168 epochs of data that amateurs have acquired. And even in that data there, you can see this 57, 58 day periodicity. If you take the July event and you look to see what the previous one was, it was actually on February the 2nd, and that corresponds to 58.5 times 3, i.e. an outburst 3 rotations later. These are the strongest outbursts, this and the 4th one in February, over the last 2.5 years. And you see again, there's a repetition here. So in recent times, the activity on the nucleus has changed rather spectacularly. If we go back to this rotational phase plot, these are the outbursts. These down here, these 4 here, are the ones that are actually showing that strong activity. And see how they're immersed in a complete sea in the rotational phase space of no activity whatsoever. This is extremely strong evidence that the periodicity really is real. And actually, if you said, well, look over here, maybe that's, if we look there, look, there's an area here which is devoid of strong outbursts. Something like only 40% of the total phase space is occupied by the very strongest 100 outbursts or so. So half of the outbursts, by applying this period, we're able to separate it out and see a periodicity. Okay, so on that note, I'll finish and hand over to Laura. I'd have to stop sharing. Okay. Oh right, coming back now. There we go.
You're on mute, Laura.
There we go. Sorry about that. Thank you all for having me. The captioning is on for my students, and I took a quick look and I couldn't remember how to turn it off this morning. So hopefully it doesn't bother you too much to have captioning on. The mission 29P that Richard talked about is really exciting to those of us who study 29P as so-called professionals. That sort of data is something we could never get from a professional telescope, that detail, and that's provides critical links between when we do study it with spectroscopy or radio telescopes to know what's going on optically when we get our observations. And additionally, we've begun to write target of opportunity proposals based on the fact that this data is available from the amateur community. So we can say, hey, there's an outburst, and we can go to one of the larger scopes and try to get spectra. So it's really exciting that Richard is organizing this and making it available so I can ask for time on places like the Keck telescope. So this picture here shows, this was our nice graphic for our mission to 29P. We chose it because, well, I personally think it's the most interesting object in the solar system for reasons that Richard has explained. It's a highly active object, but why do we care? Well, it comes back to learning about the formation of the solar system. And the small bodies in the solar system are the least processed bodies in the history of the solar system. The planets, they've all been evolved by gravity, by geology, by multiple factors. So the chemistry has changed. The surface features are not due to primordial conditions. However, we think the chemistry of the small bodies may be closely related to primordial conditions. Of course, there have been processing over the history of the solar system, but far less so than for any of the planets. So, and then of course, these bodies are what originally accreted to form the larger planets. So if we can find out more about the small bodies, we can find out about what created the larger planets and hope to tie everything together in terms of how did our solar system form? How much mixing was there? So the more we learn, the more complicated we learn it is. We were hopeful back 20 years ago that we could look at the composition of comets and divide them into different classes and hope to figure out where they came from. And initially it looked promising that there were two different groupings of comets chemically in the optical observations. And then we started making infrared observations and radio observations and realized, wow, this is really complicated. And the more modeling we do about the history of the solar system, the more we realize why that would be. The giant planets have migrated over the history of the solar system, and in their migration have tossed the small bodies around and scattered them around. But it's not hopeless, right? The more we study the composition of the small bodies of the solar system, the better idea we get of how much mixing might there have been, right? We can't figure it out until we actually start to study. And the best way to figure these things out is to actually go to these objects. Right? We can observe them from Earth, and the Jupiter family comets, we can, as the closest objects to Earth, we can study them spectroscopically. They've been visited by multiple spacecraft. So they're the easiest ones to get to by spacecraft. So we've had multiple spacecraft. The Rosetta mission was utterly transformational to cometary science. We learned so much more about how comets works, what happens, what an evolved Jupiter family comet looks like. But this is the Rosetta Comet 67P is a very evolved Jupiter family comet. If we want to know what Rosetta tells us about solar system formation, we need to know how has it evolved? How did it get to the surface it has? How did it get to what we have observed and what we've learned from Rosetta? The closest we have to a primordial body, well, in fact, the primordial body we've visited was New Horizons, flew by a Kuiper Belt object, Arrokoth. Now, this is not the kind of object that becomes a comet. It is what we call a cold classical Kuiper Belt object. It's in a near circular orbit. Its orbit does not get perturbed by the giant planets. So this is not the kind of object that becomes a comet. So, but it's the closest we have to what might a comet progenitor look like. So how do we get from Arrokoth to 67P? Well, to figure that out, oh, here I've got a nice comparison here. 67P. This is size to size scale. So 67P. While they have some similarities, they're both bilobed object. 67P is much smaller than Arrokoth, and of course, the surface is very processed. So, getting to a Kuiper Belt object is really hard. Right? New Horizons got there after a very long time. You can only do a flyby, at least right now you can only do a flyby. Doing an orbital study of even Pluto is very expensive, but there is a class of objects that are somewhere in between the Kuiper Belt and the processed Jupiter family comets. There's a long period of comets for which European Space Agency is developing a mission to go to a comet that's come in fresh from the Oort cloud. It's going to hang out until a comet comes in. So that's an exciting mission. But the other option is to go to a centaur. So centaurs are these class of objects that are between the Kuiper Belt and the Jupiter family comets. So Jupiter family comets are comets that are in the plane of the solar system predominantly. Their orbits are governed by interactions with Jupiter. Their perihelion distance is inside of Jupiter. And so these are the ones that have shorter periods, predictable. We can get to them inexpensively with spacecraft. We can observe them easily. We know when they're coming. And so that's why all of our spacecraft have gone to Jupiter family comets. Centaurs have perihelion outside Jupiter and aphelion inside of Neptune. And what happens is the Kuiper Belt objects get the ones that are being gravitationally affected by the giant planets. They get scattered in to the region inside Neptune, and then the giant planets start playing pinball with them, scattering them around. They spend a few million years in this region, after which some will get scattered back to the Kuiper Belt, some will get scattered out of the solar system, and some will get scattered into the Jupiter family comets. So we wanted to go to 69P, because it's one of the most interesting objects in the solar system. It is a centaur. It is always active. It has these outbursts that Richard told you about. And by going to 29P, we would get guaranteed the chance to study an active centaur, right? Centaurs beyond Jupiter, it's too cold for water to be providing the activity. Jupiter family comets in close to the sun, water sublimates, water drives the activity. Out beyond Jupiter, what drives the activity? Well, Richard has had multiple hypotheses. There are ones beyond the one he has. Amorphous crystalline water ice, CO activity. There's all sorts of pros and cons for each of these, but we really don't know what's causing it. And honestly, I don't think we're going to know until we visit a centaur. And this activity is one of the things that gives us this huge clue to how do we get from primordial to Jupiter family comet. Trying to keep it on time here. So as we were proposing our mission, or developing our mission to go to this object, because we want to go to a centaur, we wanted to study the evolution from Kuiper Belt to Jupiter family, what's the in-between state, how do we draw these evolutionary ties back through time from our well-studied objects to the objects that are really hard to get to. What we discovered is something really interesting is going on with the orbit of Schwassmann Wachmann 1, 29P. So when we first were thinking about going here, well, it's active. It's got a near circular orbit just beyond Jupiter. We thought we could get to it and actually orbit it. Orbiting it is really, really hard, but we had a chance. And we did find the orbit. And the orbit depends on an encounter with an orbital encounter with Jupiter. That the spacecraft has to go past Jupiter at a certain time to change its inclination, but it also has to be, Schwassmann Wachmann 1 has to be in a specific location relative to Jupiter to get there. And what we realized is that this also changes the orbit of Jupiter. Not that this was unknown, it's just that nobody was talking, sorry, not orbit of Jupiter, our orbit of 29P. Not that this was unknown, but it was, nobody was talking about it, nobody was thinking about it. And one of our team members said, hey, did you know that this encounter, this thing we're using, this changes the orbit of 29P? So this caused some frantic scrambling. Oh no, is it going to, because it's going to become more eccentric, it's going to get too far away from the sun. Our mission would conclude in the time period when we're still close to the sun, close enough to the sun to expect activity, and everything was fine. But in the process of studying that, what we learned was that that Schwassmann Wachmann 1 has a really special orbit. So the orbit, so it came into its current orbit, near circular orbit, in 1975. It's leaving in 2038, and 2038 was the year we would plan to arrive there if we can get launched on our rocket big enough to get us there now, which is not likely. Well, but we haven't given up. But there'll be the next conjunction in 2038. which is going to increase both the semi-major axis and the eccentricity of Schwassmann-Wachmann 1. So in 2038, there's a chance its activity will be changing, or probability. And so that's one of the reasons we really want to characterize it really well now, because we really want to see what happens at 2038 as it slowly begins to go further from the sun. And that might give us clues to what's causing the activity. Okay, and okay, I'm sorry I don't have, okay, see where my timing is. Okay, so these plots, so basically what we did when we realized this is we started to do dynamical modeling. Fortunately on our team, we have some really great dynamicists, Gal Sarid, Kat Boak, Jordan Steckloff, and so they started modeling the orbital history of Schwassmann-Wachmann 1 using a method where you use many what they're called clones. So you put a whole bunch of objects in Kuiper belt, both what's called the scattered disk. Those are the objects in the Kuiper belt that are perturbed by the giant planets, and what's called the cold classical, which is objects that are rarely perturbed by the giant planets. And we let them evolve for millions of years, and took the percentage of those that came into the Centaur region, so came into inside of Neptune, and then changed how we were letting them evolve. Instead of just, now we started taking shorter time steps and letting them interact with all 4 of the giant planets and seeing how they evolve in the Centaur region. And what we were interested in was how many Centaurs transition into the Jupiter family comet region. What we found, and this is just an example orbit of a Centaur. So A is the semi-major axis, Q is perihelion, big Q is, little q is perihelion, big Q is aphelion. And this is just an example. So you can see, while it's a trans-Neptunian object, it stays pretty stable. And then all of a sudden it shifts into the Centaur region. And now that it's interacting with all 4 giant planets, its orbit starts changing rapidly. And the average time in the Centaur region is millions of years. Some fraction of those Centaurs transitioned into Jupiter family comets, which is what we were interested in. So we wanted to know what was the chance of Schwassmann-Wachmann 1 becoming a JFC in the future. And what we discovered is, is that 21% of the Centaurs enter this region here. So this is the semi-major axis of a Centaur versus the eccentricity of a Centaur. The heat scale is how long it spends its lifetime there. So most of the Centaurs spend most of their lifetime with relatively large semi-major axes and some eccentricity. So this is the majority of the Centaurs. But there's this one region here, what we ended up calling the gateway region, where they only spend a few tens of thousands of years, or a few thousands of years. Try to get my time scale right. And this is where Schwassmann-Wachmann 1 is. And the interesting thing we found about the objects that enter what we ended up calling this gateway is that more than half, 70% of Jupiter family comets spend time in this region. So objects that are Jupiter family comets have either come into Jupiter family comets from this region, or they left Jupiter family comets and entered this region. You have to remember with dynamical simulations, you're integrating one way, but it's just, if you integrate one way, it can go back the other way as well. So we can't distinguish between going in and coming out. But most JFCs go through this region. And so what we found is, so this line is eccentricity 0. And so these objects here, these dots are the black dots are objects that are Jupiter family comets by what's called the Tisserand parameter. It's a parameter that measures the interaction with Jupiter. The yellow dots are another definition of Jupiter family comets. And we ended up defining Jupiter family comets by a perihelion distance and an aphelion distance. So we said an aphelion no further than about 7 AU. So, and this is what we call the gateway region, the orbital region through which 75% of Jupiter family comets spend some time either in or out. Right now, there are, we've plotted this for our paper, we plotted four objects. We actually now have 5 objects in this region. One of them, LD2, which is about, I can't remember the number that goes in front of it, is about to become, in the next 40 years, it should transition into being a Jupiter family comet. Schwassmann-Wachmann 1 has about a 65% chance of becoming a Jupiter family comet in the next few hundred years. But when we integrate its orbit forward and backward, we can't go beyond about 700 years forward or backward before chaos says we don't know what's going to happen. But it does have about a 65% chance. And if it does become a Jupiter family comet, it will be the biggest, brightest one in history. And we're also pretty sure it's never been one, because if it had, it wouldn't be as bright as it is. Okay, I'm running out of time. So the exciting thing is we found this region where centaurs are likely to become Jupiter family comets. So this has become a really interesting region to study centaurs. Any centaur that's in this region, it would be interesting to get light curves of. Because any of these objects become actually interesting spacecraft targets. Not as interesting as 29P, but they are all actual potential spacecraft targets if we want for our dynamical evolution arguments. Okay, and then this is just another plot showing that 29P is super special. Its activity level, this is 29P's activity compared to activity versus heliocentric distance, and it compares to that of long period comets rather than with some other centaurs. So it's extremely active object, which is why we're so excited about it. It's the only centaur we're guaranteed to find active. Okay, so so our mission did not get selected for advancement in the last discovery round. We were rated category 1, which is recommended for development for flight, but we weren't the highest NASA priority for where should NASA go next, so we did not get selected. However, we are on the list of interesting missions, so we get interest. We're not dead. There continues to be work to develop orbits for future proposal opportunities. It gets harder and harder with time. We need bigger and bigger rockets. We need more and more creative propulsion methods to get to our transition. Basically, any way we get there, we need to arrive in 2038 to make that orbital conjunction that allows us to go into orbit. One possibility would be changing our mission to be a slow flyby instead of an orbit, which would be disappointing, but with 29P as active as it is, a slow flyby could still be interesting. So if we miss that conjunction, we might be able to do a slow flyby. I don't know if that will be as compelling as a 2-year orbital mission, but so basically the argument we made is that our mission would fit in between all of these great missions to Jupiter family comets. And then these missions to the outer solar system, New Horizons is now complete, but ESA is developing an interceptor to visit a long period comet fresh from the Oort cloud. NASA is sending a spacecraft to Trojan asteroids. So outer solar system objects, where does a centaur fit in between in this evolutionary story? And I'm about out of time. So our orbit was secret. It took 2 years to find, so I can't tell you, though I've told you it involves a conjunction, so you can, if you can at least sort of go figure out what that conjunction was. But it doesn't, but if we miss it, it doesn't happen again until 2083. So given we took 2 years to find this orbit, we're not, yeah. Let's see, and yeah, this is the orbits we had. It was 2 years of orbiting, studying the well, here I've just called them cryovolcanoes, studying the outbursts, trying to determine what causes this. What does the surface look like? What is the surface composed of? So hopefully we'll have another chance to propose, and I should hand it back to Richard.
Hi, Richard. So thank you, Laura. That was really interesting. So, Richard, we'll take questions in a few minutes. So
yeah, remember, I'm just going to finish off with the very latest from the amateur work, because I need to acknowledge the contributions of all the individual observers and things like that.
That's great. So we've got 20 minutes, but I'd like to have some time for the questions as well.
Yeah,
so
but I'll be quick.
Grand. Okay, thank you.
Okay. Done. Just trying to get it to go forward. I think I'm going to just try that again. I might have to. No, I've got to stop it. Just hold on. Right. Yeah. Just before we go to questions, what I wanted to do was to show what success we've had in catching 29P before it starts an outburst and watching it through outbursts. This is the holy grail, really, for some amateurs for the past 4 years, most notably Jean-Francois Soulier, a French amateur. So here's this plot I showed of the last apparition, and on here you'll see these are the amateurs who have actually contributed, and their totals for the number of observing runs that they've done. So thank you, everybody. I would like, actually, if we had time, to talk about each and every individual who's contributed to this, because each one has done so well in their own different ways. As to capturing outbursts, we've had success with 4 occasions, once in 2017, once in 2019, and twice during the present apparition. So here's an example of the 2017 event, when some 9 different observatories contributed to this. So this shows the power of people working together, and that includes one, well, professional, the Trappist observatories in Morocco and Chile. Those are shown in red. But the best light curve came from the November 19 event, which is shown here. And this was discovered independently by Jean-Francois Soulier and by our Comet section director, Nick James, his very self. He started apparently some 30 minutes after the outburst actually was triggered. But fortunately, Jean-Francois, who operates a remote observatory in Haute-Provence, had already started more than an hour before Nick. So he actually has got a lead in to the actual outburst. Now, Jean-Francois' observatory is a 20 centimeter, which he operates remotely. And this is a frame of a video that he's created based on 1-minute exposures during the first few hours. So I'll just see if I can switch to the video. I think I might have to stop share screen. Right. I think you can see that now. Let's see if it'll run. Yeah, there you go. So what we're looking at here is consecutive 1-minute exposures speeded up a great deal. And the first few seconds you can see before the the comet is quiescent, but you see it get brighter and brighter. And of course, it's moving all the time as it tracks across the sky. And the analysis of these individual frames using Gaia photometry was a way in which it was possible to actually measure what it was doing. This actual achievement is quite remarkable when you think that, you know, you might see 2 or 3 strong outbursts in 1 year. Last year, I think there was only 1 or 2. And so to actually be observing at the time, and it was actually quite close to opposition, which was another fortunate thing. So it's going to be a while before anyone achieves equals this particular feat or exceeds it. Okay, so we'll stop that. We'll go back to the slides. It always has a hiccup here. There we go. And this is the light curve that we got. You can see the quality of it is very, very good. And it's because of that quality, it's possible to actually start to model what was going on during the outburst. And another thing that happened, as well as both Nick and Jean-Francois, Nick sent out an alert to all the other observers that very evening. And so lots of other people got involved and contributed. And the next light curve is what it looked like over an 8-day period before and after the event. So you can see the sharp rise to maximum light from a quiescent stage, but you can also see the fall off. And what's interesting is this feature here, which actually also was hinted at on that 2017 outburst, that it seems to, if we look at that more closely, you see this change here. And my hypothesis is what we're seeing is that some of the debris that's ejected is actually waterized, and it takes a day or 2 for that to sublimate in the heat of the sun. And we're seeing loss of intensity from the loss of that water ice. So about 5 days later, this is what the coma looked like. And you can see again this Pac-Man shape. And what we could measure was the speed at which the debris was moving outwards. And if you plotted that against the fraction of material that had appeared, you could see you always get this linear effect, and that the outer edges of the coma were moving at about 150 to 200 meters per second. So that's typical of a strong outburst. Now, the analysis can also be done of the photometry. Instead of doing magnitudes, you can actually work out what the extra light was due to the outburst, and you can express that in an absolute sense by converting it to the equivalent areas of the nucleus itself. So this is the early part of the outburst, and then if you look at the entire light curve on intensity grounds, you see that it actually eventually became 31 times brighter than the nucleus alone. Okay. It's possible to model the event. I'll skip through this very quickly. The red circle is the imaginary cloud, ejector cloud, and it's opaque in the early phase. So you need geometry. You could go through an increasing size coma and actually calculate what the light curve should look like before the cloud starts to become optically thin. And this is a fit, one example. It's a case where the source is quite close to the terminator. It's only 5 kilometers from the edge of the nucleus projected on the sky. And what this gives is a measure of the average expansion velocity, which was about 57 meters per second. So that's quite a nice fit. You can also model the later stages when the coma starts to become optically thin. And with the model, you can calculate the transmittance against the the actual amount of light you're seeing as the coma expands, because it gets gradually, thinner and thinner. And this also seems to show that we're losing intensity after the first hour or two. And this, again, I hypothesize is the water ice disappearing. Now, finally, I want to just mention the concept that some of this debris that's thrown out by the comet actually gets pulled back by its own gravity. The nucleus is so big, it's 64 kilometers across, that anything moving less than 20 meters per second will have to fall back onto the nucleus. And what we found this apparition using the 2-meter telescope images, that we actually could see this taking place in real time, in a sense. The debris, the cloud, is actually extremely black. So here's an example of the carbonaceous chondrite, which is representative of the grain. It contains the grains of what a comet's coma is like. And this material, if it's moving too slowly, will fall back. The 2-meter telescopes are a consequence of the initiative that an entrepreneur called Dill Fawkes undertook in the late 1990s. And it is his vision of having several 2-meter telescopes that schools and colleges could use as a way of promoting science and teaching of engineering and technical subjects for young children and pupils. And you can see the scale of this, and it is this telescope that's been able to allow us to look at the innermost coma of 29P. Here's an example of a time series taken with one of these telescopes, plus some of the 1-meter telescopes in the Las Cumbres Observatory network, which the Fawkes telescope is now part of. And what you're seeing here is the nucleus. It's only a 50 arcsecond square bit of sky. So you're looking at the center of the nucleus, and you can see how over just 3.5 days, the coma develops. And it's studying the photometry of this inner coma. We're using apertures of gradually larger size that we're able to piece together the actual distribution of light in that inner region. And I've only got 2 more slides, I think it is. I'll show you 2 examples of why I think we're seeing fallback onto the nucleus. These are largely 2-meter images, and what you do is you use different size apertures, and that represents distances of about 3,000 kilometers up to 20,000 kilometers. That equates to 1 arcsecond radius to about 6 arcseconds radius or so. And if you do that, you can actually normalize the photometry with stars and get really accurate data. And this was the first discovery, that you see that after a few days, you get a relatively fast change where you're losing light in the inner coma. And what happens is the coma relaxes back to and stays around this limiting light curve. And what this is it points actually back to 0 radius. That's the brightness of the nucleus alone. So, and the rest of the coma is gradually moving out. It's still moving outwards. So the final coup de grace, so to speak, is when another outburst, in August the 22nd, showed this characteristic. So after about a day and a half where it had brightened, it was this bright at the very inner coma. What we saw over a 2-day period is a rapid fall off, and then it stopped losing intensity. So the material had fallen back down and it stopped, but it stopped before actually you would expect. But then after a few more days, another rapid fall in brightness. And then again, it stopped on this characteristic line, which points back to the bare nucleus. And it seemed mysterious, this, but I went back to the light curve data that the amateurs and some of the telescopes had got. And it turned out that instead of there being 1 outburst, there had actually been 2 outbursts within the space of less than 35 hours. And what we're seeing with the inner coma is we're seeing the fallback from these two events taking place one after the other. And that's really led us now to think that next year we can do a lot more. And in fact, we can look back at the archive of data that we already have and start to piece together all the different types of fallback. And it really would be interesting for professionals who would model the orbits, because to be able to suspend the debris for a few days before it falls back can't be done with a simple model of a spherical nucleus. There has to be something strange going on to be able to sort of levitate a certain amount of the coma before it then falls back. Whether that's a second object in orbit or something, something quite different, I don't know. But on that note, I'll stop for questions.
Thank you, Richard. In fact, thank you both of you for a fascinating talk on an absolutely incredible object. So we've got a few questions, but before we start on the questions, I'd just like to do a brief plug for Richard's Mission 29P web pages, which people can get to from the Comet section website. If you go there, you'll see a lot of the results that Richard has talked about today, and also there are links to the Comet section observing guide, which will tell you how to observe this fascinating object. So Richard has developed a standardized way of doing the observations, and that's all in the observing guide. We have a bit of a break over the summer months because the comet's currently in conjunction, but it'll become observable again in the autumn. And that's the time when we really need people to observe it, because it'll be in the morning sky, and fewer people tend to observe in the morning than the evening. I don't know why. Okay, so we've got a few questions. One from Darrell Dobbs is saying, has anyone taken spectra of 29P to see if it differs from other comets? If either of you would like to comment on that.
I can comment on that.
Yeah, thanks.
So yes, we have taken spectra of 29P. It is very distant. So it is as bright and active as it is still very hard to do spectroscopy of it because of its distance. So I've taken visible spectra with Keck Observatory, and all I observed was the continuum. We didn't see any gas in the optical. In the radio wavelengths, carbon monoxide has been observed. There's a paper just out this last week, I think, on Spitzer observations. Actually, the Spitzer observations there's Spitzer spectroscopy and images that measure CO2. So the CO2 is pretty similar to Hale-Bopp, so that's normal. But I'm hoping that with this detailed monitoring that's going on, that I can get a Keck target of opportunity chance to take a spectra and see if we can detect some other species and see what it looks like.
So have the spectra so far mainly been with the object in quiescence, or if you managed to get it?
Right. So yeah. So you just get time randomly, and it just hasn't been in a big outburst. So we want to say, oh, it's in a big outburst. Let's trigger our observations and take spectra now.
Yeah. Well, hopefully with Richard's program, we're monitoring it sufficiently now that we can alert you very quickly.
And then hopefully the tax will think it's exciting enough to give us time. So yes.
Yeah, indeed. A question from Kai Stoddard-Jones for you, Laura, about the Chimera mission. He says, if the mission went ahead, but it was only a flyby, how much observing time could we expect to have?
Yeah, so if we could do a slow flyby, which means slowly approaching it to, I don't know if you can see me, I can't see myself.
Yeah, we can see.
Okay, you approach slowly and then you slowly go away because you're only going at a slightly different speed than the comet around the sun. You actually get a couple of months, right? Because you're observing for several months on the way in, and it gets better and better and better. So you actually get, of course, the flyby itself is relatively short. It's only just like, it's only a few hours long when you get your highest resolution, but you get really good resolution for a couple of months. So a slow flyby is not bad.
Yeah,
not
so we're not talking
orbital, but it's not bad.
Yeah, we're not talking about a kind of fly past Pluto where you have a few days. It's a a few months, and there's a good chance of having at least a small outburst in that time.
Yeah, and there would be a good chance of having at least a small outburst in that time. So yeah,
okay,
still an interesting mission.
Another question from Daryl Dobbs, which is a really interesting one, about, is there one main active area on the surface or several, and do they switch on and off?
Let me, can you hear me? Yeah. In fact, what we've discovered in the last few years is that there's two types of activity. One is the strong outbursts, and the other is where there are lots of much weaker, what we call mini outbursts. And there, in the last few years, there has tended to be only one area which has had strong outbursts. In a few more years' time, if the thing is what period is periodic, every 15 years it comes back to the same place relative to the sun, and it's at the same season. We might expect just in a few years' time for the activity to start to really kick off again. But at the moment, we're in this sort of transition. We've had a very large number of these mini outbursts. And the interesting thing, although they're not so sexy because they're not so strong, what happens is the proportion of material that's thrown out, more of it falls back onto the surface. And so it reforms the surface. And this is fundamental to explain why the comet is as it is. And maybe we can, we can do another talk about actually what's going on and why these things switch on and off as you ask. So yeah, it's just full of interesting things, and there are two types of phenomenon going on there, I believe anyway.
So I'm interested in thinking about, if the Chimera spacecraft was in orbit around 29P and it was all quiet, and all of a sudden one of these really big outbursts happened, and from what we can see from the light curves, they are really sudden. They're kind of explosive outbursts. What would the spacecraft see? And would it be in danger?
Right. So we worked long and hard on the would it be in danger question. And so we developed this orbital model where we started off at a large orbital distance and gradually brought ourselves in closer and closer. And we have a paper that will hopefully be accepted for publication after this. We've just turned in the response to the reviewers, showing that with the amount of large stuff that would actually be dangerous to the spacecraft, that our initial orbits were well outside the region with which we would have to worry about those. And the thing about orbiting, as with Rosetta, as you know, Rosetta didn't run into anything that hit it, anything large at least. Basically, it's like driving through snow. It's, you've got, mostly you're running into little things that are just gently at orbital speeds, just gently encountering. It's not like a flyby where you're going at a high velocity relative to these things. You're very similar velocities. So our bigger orbits would have told us if it was safe to go into our more close-in orbits. And yes, we would have been disappointed if we could only do relatively low resolution. Well, but we were hoping to be able to do up to the highest resolution that Rosetta got. Mm-hmm. But on average, our data would have been at this sort of resolution of that Rosetta image compared to the Arrokoth image. Of course, 29P is larger than 67P. So yeah, we were preparing for that.
I mean, it would be just an amazing thing to see, kind of one of those large.
And if there were very large boulders in orbit, that would have been exciting too.
So I think that the main problem with Rosetta was, as you say, driving through snow. It was just confusing all the star sensors, and it was causing problems with attitude control, which is why they had to back it off.
Right.
Okay, just one final question then from Kai Stoddard Jones, probably to Richard, this one. How is the coma radius calculated from observations, given that the coma has not got a solid edge to it? What's the criterion for determining?
Oh, right. Well, you don't need to calculate radius. What you do is you calculate the cumulative intensity for a given radius. So it's the total amount of light within a certain radius measuring aperture. And you can do that for lots of different size apertures. And that way you can piece together the whole cross section of in terms of the light that's being reflected off the coma, depending on where it is relative to the nucleus. So you don't talk in terms of a specific coma radius unless really, yeah, I think that's fair.
Yeah, so I think again, for anyone who's got any questions on how to do the observations and how Richard goes about doing the analysis, just have a look on our webpage, and I think there's a pretty good description there. So that was really fascinating talk. Thank you both very much for that. Thank you, Professor Woodney, for your contribution as well, all the way from California. Right? It's kind of
for having me.
Morning for now, and thank you very much, Richard. And personally, thank you from me as Comet Section Director for running the 29P project on probably one of the most interesting comets in the solar system, I think. So that's the end of this webinar. The next one, and I always really ought to check this before I do the next webinar. The next webinar is actually on June the 9th by Howard Bannock, talking about sketching deep sky objects. So hopefully you'll join us then. Again, 7 p.m. on Wednesday, June the 9th. In the meantime, there is, I think, a BAA meeting, isn't there? Yes, there's the George Alcock Memorial Lecture, which is coming up on May the 26th. And that is being given by Jonathan Shanklin, who's my predecessor as director of the Comet Section. And he's talking about George Alcock Goes to Antarctica. So anybody who knows Jonathan will know he has a connection with Antarctica. Even more so now, I think there's a glacier that's named Shanklin in his honor in Antarctica. And there's not many Comet Section directors who have features in Antarctica named after them. So hopefully everybody will join us for that. Again, thank you both for a really interesting evening, and enjoy the rest of your days. Thank you. Cheers.
Bye.
Bye.